In this video, we're going to look very specifically at kinetic energy. So look at this picture. Got a plane flying, got some kinetic energy, another plane flying, got some kinetic energy. In fact, a lot of things moving has kinetic energy. So, hint hint, kinetic energy has something to do with stuff that move. So, what is kinetic energy? Well, I mentioned it. It's energy of a body or object due to its motion or speed. Okay, if you're moving, you got kinetic energy. If you're still, you're chilling. So you may have seen before the kinetic energy. Oh, by the way, we often say kinetic energy as sometimes you can say energy kinetic, or you may have seen it before as what is it called, K.E, kinetic energy. Both works, depends on how you want to define it. I will usually use a lot of EKs, so look out for those. So you may have seen before kinetic energy is half mv squared, right? You may have heard that before. We say, oh, Ke is half mv squared. But where does that come from? How does that relate with the work done and all this stuff we've looked at? Well, here's the origin story for kinetic energy. And take note. You will need to be able to tell this origin story in an exam. In other words, you should know how to derive the half mv squared and say where it came from. Okay, so let's say we have this good old block pushed along from one side to the other. Okay, you have some force acting on it, and the same force push it a certain distance. We call displacement S. So this displacement S. Okay, so what's happening here? So we're doing work on the box. Okay, so this red force doing work on the system. That's how we call it. So we're doing work on system. What is a system? In this case, the system is the box. Okay. We assume it's a frictionless surface, so it's smooth, so no other forces are acting on this system. Just that constant F force. Okay, so now we say, okay, work is a change in energy of this system. So we can say work is the change in kinetic energy when it's in the beginning position and then it moves to the right. So we also know from our previous video about work done that we can define work done as the force times the displacement. Here, F and S are in the same direction, so we can just write F times S. Okay. Now, we're kind of stuck here. F times S, that's it. How do we change that into half mv squared? Now remember, Newton's second law. Ding ding ding, ring some bells. So what if we plug in a specific form of Newton's second law in? This specific form means the mass is not changing, so it's still the same mass in here. If the mass is changing, then we'll think about changing momentum and other stuff. So don't worry about that. Mass is constant. What if we plug this in here? We will have MAS, mass. This looks very strange. Doesn't help me a lot. But what if? Is there a way to find the acceleration of this box with maybe some kinematic equation? Let's see. So the box starts off with some initial speed u, ends up with some final speed v, and because of that force acting, there's going to be some acceleration of this box. So quick check. I have V, U, A, and S, so I could use the Stuva or kinematic equation, V squared U squared plus 2AS. Rearrange to plug A into this equation. So if I plug that in, I will get AS. Well, I guess I could plug AS in. Nice. Save me some work. If I plug in AS, what I'm going to get is V squared minus U squared over 2. Now, that looks very strange. But if I say, for this particular system, I set my initial speed to be 0. U is 0. So if U is 0, then the U is gone. All that's left is half mv squared. And this is the most common form we have seen this kinetic energy appear. Oftentimes we say it's EK, but actually in the true story is that it's a change in kinetic energy with reference to 0. So we're saying speed of 0 is the reference point, 0 kinetic energy when you have a speed of 0. Okay. Now this works, except that sometimes in A-levels you may see questions where the initial speed is not 0, but you want to find a change in kinetics, so that's fine. Just note that the initial speed may not always be 0, but if we assume it's 0, you have this half mv squared. And you need to be able to show how do we go from the work done idea to this thing. So you need to be able to derive this. So you can memorize it, but try to understand what's going on here. What's plugging in. We're plugging in two things. Newton's second law and a kinematic Stuva equation. And we have half mv squared. Da, 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 da. So beautiful. Anyway, so here we have a force acting, doing work on a system, getting it to go faster. So there's an increase of energy in that box, kinetic energy increase. You can summarize that in a table like this on the right side. So firstly, if your box is getting faster, like in this case, it's increasing in speed. So we can say the speed is increasing. Means there's energy transferred to the system. So to the system, which is the box. So your box is gaining energy, okay? There's a force acting on it, and that force is transferring energy to the system. Work done, in other words. So work done, if you calculate it, should be a positive value. So I don't know, maybe you could calculate it to be, let's calculate. Let's say it goes from 0 to a velocity of 5. So the work done on this box, if I use the example, will be half mv squared minus half mu squared. Well, u squared is 0. Okay, great. So we don't need to worry about that. Then you are increasing the work done to, let's say this box is 2 kg. Increase to 5 meters per second squared. So what would that be? So that'll be 1, just 5. So 5 squared will be 25 joules. And if you want to make sure you know the signs, you want to say it's positive 25 joules. So work done is positive. It makes it go faster. So what if there is a force that makes it go slower? Okay, this one we'll save it for later. It's something to do with friction. But if there's if your box is getting slower, oh no, it's losing kinetic energy. So we can say energy is transferred from the system. Some kind of force is taking that energy away. So if you do calculate the work done by that force, it's going to be negative in that case. Okay, so yeah, we'll save that for later, but just so you know, how do you know whether work done is positive or not? You look at whether the speed is increasing. Or you can look at how your kinetic energy is changing. Energy transfer to system means your system will have more and more energy, move faster. Transferred from system means, losing energy, no energy. Okay, so that's the main idea of kinetic energy. Oh, let's look at this example of a short part. A short part is that metal ball. Metal ball, they're like kind of 1, 2, 3, and then they throw it. But the athlete will have to push that metal ball for some distance to give it some energy, get it going. So, okay, so we have a metal ball, and this champion is exerting a force on it. Okay, I should push this side, mirrored. Okay, he's pushing a force on that ball. And this ball is 7 kg. Okay, let me label this 7 kg in a straight line. So the ball is going to move from rest. From rest means initially its speed is 0. Notice why I say speed, because speed is a vector, because energy doesn't really matter in this case. And you end up with 12 meters per second. Why I write 1 over 2? 12. Sorry about that. 12 meters per second. In a distance of 1.2 meters. So try calculate it out. What is the average resultant force on the metal ball? We didn't say change in energy or work done. What's the average resultant force? Okay, so hopefully you got a chance to try out a little bit and see. So first things first, you may be very tempted to say, F equals ma and all this stuff. But there's a reason why they say the word average resultant force, because we don't know if that force is constant or not. It could be changing. We don't know. So that's a problem. So we don't know if force is constant, but no worries. Let's write down what we do know. So we know that work done is force times a certain displacement. Now here the force is the same direction as displacement, so all is good. Okay, they're parallel. Don't need to worry about cos theta or things like that. Because if you do write cos theta, theta is the angle between F and S, which is 0. So cos of 0 is just 1. So this one just becomes 1. So it's pretty much insignificant. Okay, so we have force times distance. Force could be different because, you know, maybe at first the fella have lots of strength and it goes oosh, but later he push less force. Anyway, we good chances force is not constant throughout the whole journey. So what else do we know? Change in energy. How about that? Let's write it down. So we know work also means a change in energy. What energy here? See, they talk about speeds, right? So a good chance is we can talk about kinetic energy. It's moving faster and faster. So kinetic and change in kinetic energy is related to the force times displacement. So we have we want to see what it changes. It goes from 0 to 12 meters per second. So half m v, oh, why is my m disappearing? V square minus half mu square will be equal to force times displacement. We can plug in all the values we know now. So half mass is 7 kg. Velocity, we end up with 12. Initial is 0. Great. Don't need to worry about that. So just minus 0 equals to that force, average force we're trying to find, times the displacement, which is, 1.2 meters. So from here, we can find the average force. So that would be about 0.5 times 7 times 12 squared divided by 1.2. So we get about 420 newtons. Keyword, let me add here, average. Okay, so average means, let's say the force starts off at, maybe it could be 120 newton. Suddenly halfway it become 80. Then it become 100 newton. We don't know, it's changing. So your force could be going up and down, but the average we estimate to be 420 based on the changes in energy over a certain distance. Okay, so if you try to use kinematics equation or Newton's second law and things like that, you will find that you won't quite get the answer you want because your force is changing throughout the whole period. So acceleration is kind of changing as well. So we can't really use those ways to solve this kind of question. Okay, so just remember, just write down what you know, this main thing, and proceed to see how you can use the information given to solve the question. Another one, this is a kind of a fun one. This one, I really want you to pause the video and try it out. It is also on page 12. For those of you who have the handout printed or want to try on a piece of paper, you can pause the video and also try it out. Okay, let's resume. So the question is, when a horizontal force is applied to a frictionless trolley, frictionless is important here. Frictionless because if there is friction force, then stuff gets complicated. We'll save that for another video. So you're pushing over a distance s. Kinetic energy changes. Ooh, we have a change in kinetic energy. So kinetic energy is changing from 4 joules to 8 joules. So that's from, so 8 minus 4 is a change of 4 joules. Okay, good to know. If a force of 2F is applied, what will the original kinetic energy become? Oh, so many words. Okay, remember my tip. Whenever there's a problem and there's no diagram, you should try to draw it out as much as you can. So here, I've drawn out for you. So in the first case, you're applying a force F. Kinetic changes from 4 joules to 8 joules. So maybe it started with 4 joules and then it goes to 8 joules. Wow, it has gotten faster. Okay, good. I think that's all we know about that. Then the second case. Oh yeah, I forgot to say this distance S. Second case, you apply 2F. So this force is kind of bigger now. I should make the arrows doubly as long as well. And over a distance of 2s, so now the distance is 2s, so you have 4 joules. What energy is it going to have at the end? This one didn't give us values to exactly calculate, but don't panic, it's probably one of those algebraic questions where you have to sub alphabets and play with it. So let's write down this first scenario, some equations, and the second scenario for that. So number 1, work is a change in energy, which is force times distance. Okay, so they already gave us horizontal force F applied throughout the distance. So you can say, okay, so the force is not changing. Force, 2F, 2F. So the change in energy, we already calculated that, is 8 minus 4. So that's 4 joules of energy. So 4 joules equals to some force times distance. Okay, that's all we know. Sad face. Let's look at the second scenario. Same thing, work is a change in kinetic energy here. No other energy changes, so only kinetic, which is force times displacement. So if we plug in everything we know, work is, change in energy is, we don't know what it is. Let me just label this as EF. F for final. So change will be final minus initial, so final minus initial, which is 4 joules, equals to, okay, this whole thing is a change of energy. The same force times, wait, not the same force. Now our force is double. So I will need to put 2F in place here. Distance, wow, double the distance also, so 2S. Okay, so all is ready. Now we're trying to find, how can we solve this problem? So 2F, 2S, multiply, I get 4FS, and EF minus 4. We have lots of unknowns, but we also have 2 equations. So let's substitute both of them together. So substitute 1 into 2. Well, I should say 1, not equals to 1 into 2. So I will have the final kinetic energy of the second scenario minus the initial equals to 4Fs. Fs is 4 from the first equation. I like this. So the final kinetic energy will then be 16 plus 4, which is 20 joules of energy. So from here we know, based on a bunch of algebraic stuff, that in the end of the second scenario, you're going to have 20 joules of energy because of a double force going a double distance. Okay, so whenever you see scenarios, number 1, draw a diagram. Number 2, don't panic, just write out all kinds of information you know about the equations, and from there see how you can solve it. Also remember, you have to do this in a pretty short amount of time, so it's good practice to just, okay, you see it, you're like, okay, this is an algebraic question, I need to just write equations. So write it out. So that's your trolley kinetic energy question. This next one, kind of a revision of chapter 4. This is on page 9, also the same page if you have the handout and want to try it out. But let's look. A ball drops on a horizontal surface and bounces, so fine. Elastically, what happens to the kinetic energy of the ball during the very short time it is in contact with the surface? Okay, this one I want you to pause the video again, take some time to read through it, go through each statement, and see which one you think is true for this scenario. In the meantime, I will draw some pictures. Okay, so we have the ball hitting the table, then it goes up and rebounds. Kind of like collisions, throwback to collisions. One thing to note, very important word, is the word inelastic. This bounces in, sorry, not in, elastically. Why did I say inelastic? Elastically, what does that mean? So if you try to remember a bit what elastic means, that is, elastic means no kinetic energy is lost during that collision. So you know kinetic energy. Oops. Why does my words keep disappearing? Lost. Okay, so after it impacts the table, same kinetic, which means before it should have some kinetic energy. After impact, it should still have the same kinetic energy. But what are they asking about? They are asking very specifically what happens to the kinetic energy when it is in contact with the surface. Okay, so during the very short time means the collision time, the time of impact when it is hitting the surface. Pop. So when it's touching the table, what happens to the kinetic energy? Ooh, let's look and see. So first one, let's look at A. Most kinetic energy is lost as heat and sound energy. Well, in real life, yes, this would have been true because, you drop something, you hear a sound. Well, maybe the table gets a bit hot, but you don't really feel the temperature increase. So yes, this will be true in real life, but in this elastic case, so you won't have this thing. This here, energy loss is what we call an inelastic collision, kind of a revision of what that means. But it's elastic here, so nope. Let's look at B. Kinetic energy decreased to 0 and returned to original value. Could be possible because it returns to its original value. So if you start off with EK, you end up with EK, it's still possible. Okay, we'll leave that there, put a question mark there, maybe. C. The kinetic energy remains constant because it is elastic collision. Well, yeah, that's possible. Okay, so maybe. Oh, there's two maybe questions. Let's look at D. Kinetic energy remains constant in what? Kinetic is constant in magnitude but changes direction. Hello? No. Kinetic is a scalar. Energy is scalar. Oh, I'm writing backwards. Energy is scalar. So no such thing as direction. Because it'd be really weird if you say horizontal kinetic, vertical kinetic, kinetic that way, kinetic this way. I don't care where you move, as long as you're moving, you have kinetic energy. Okay? So now we are stuck with a dilemma. Is it B or is it D? The truth is, both are correct, but one is most accurate for this question that they are asking. So, moment of truth. They are asking what's happening to the kinetic when it's in contact. So means, if I redraw, in contact means when it's touching the table. What happens to the kinetic energy? Well, you could say it starts off with some EK, but there will be a moment when it's not moving at all. Okay, if you feel like, are you sure, miss? Go and check out slow-mo videos of colliding objects. There will be a moment, a very short time where this, let's say my fist is coming, collide, does some weird thing and then rebound. So there'll be a moment where it is not moving. What is it doing? Well, if you look at these slow-mo videos, for example, the one of a golf ball colliding, you see the golf ball come in, hit, it just does this toing and then bounces off. So what is this toing, hit, toing, and then bounce off? That's what we call some potential energy is stored in that object. So if I draw it out, maybe it hit off, then it become toing, but it didn't lose energy. It toing, but it didn't lose energy. Then it become round again. I try to draw it round, and then it takes off and leaves the table. Okay, so maybe here it approach the table, touch, toing, and then leave out. So I don't know how to say toing. What is toing? Toing is that thing lah. This bouncing, squashing thing. So it deform. Deform is the word. Hashtag deform. Deform means toing. So you start out with some kinetic energy. Then the kinetic energy becomes 0 during this period where it's deforming. Then the kinetic energy will return to whatever speed it was moving at in the beginning. No energy loss ma. Usually it's lost, but in this case it's elastic. So actually B and C correct, but B is the most best choice you can make here. Kinetic energy decreases to 0 when it's touching the table, then it returns to its original value. So in other words, at first you have kinetic energy, which is transferred to what we call elastic potential energy. Kind of like squishing a rubber ball. Okay, elastic potential ball. This is what happens when I try to talk and write. Elastic potential energy. And then once it's done its deformation and thawing, then that elastic potential energy is transferred right back into kinetic energy. Nothing lost. In real life it will, but in this case it's elastic. So this is what happens here. A lot of us will oftentimes choose C, which is wrong in this case, because there is a better answer for what they are asking when this ball's in contact. Okay? Now these last two questions are also kind of like revising earlier chapters. In fact, this projectile thing is from chapter 3. Good time to start revising stuff from last time. So let's see. We have a projectile launch at 45 degrees. By the way, this is on page 9 if you want to try it out on the handout or you printed it. But I want you to read this carefully. Choose something, anything. Just try to solve it. It's a very fast one. Well, it might be fast. And then come back and see if you got it right. Because this is also another one of those questions where almost everybody got wrong on first try if they didn't think carefully about it. Alright, so go think about it carefully. Take out your old chapter 3 notes if you need to. Pause the video and come back. So first things first, if you did not, please remember to draw a picture. So if you have a projectile launched at the angle, let's say this round thing is a projectile, and it goes, woo, flies up, comes down. So this launch is at 45 degrees. And they're asking us what is the kinetic energy at the highest point up here. Oh, also, if you didn't notice, air resistance negligible, so you don't have to worry about drag force, air resistance, and all that kind of stuff. So if you start off with the kinetic energy E, what will be the final energy up there? Now don't straight away go and say, oh, start with E, end with E lor. No. You have to think a little bit more carefully. Is potential energy involved here? No, you don't have to involve potential energy. You can think about kinetic energy. Here's how we can think about it. At the bottom, you start out with some velocity V, right? At the top, you still have some velocity V. So it's not going to be 0. But this V is different from the initial. Oh, I should change it to U, sorry. So differentiate. You start with U and you end with V. What are the components at the top? So we have Vx and Vy. One of them is 0 at the maximum height. If you forgot, time to revise a bit. At the maximum height of a projectile, the vertical component of velocity is 0. Horizontal is still the same as the beginning, Ux. Which means the only thing contributing to the kinetic energy on top is the horizontal velocity. So it's half m, well, the v there will just be Vx. So Vx squared. But how are we going to find the answer? Because you look at the choices A, B, C, D at the bottom side, it's in terms of E. Okay, so we need to think about initial condition. So if I break down my initial velocity, here we go. Let's say I have this initial velocity U. The Uy vertical part will be, actually we don't need the vertical. Let's look at the horizontal. Horizontal part Ux is U, what is it? U, cos or sine? Adjacent, hypotenuse. So U cos 45. Which is, cos 45 is root 2 over 2, but I'm going to check and see. 45. Root 2 over 2. So root 2 over 2 U. That is the initial horizontal velocity. Then the vertical, you can find it also lah, but we really don't need it. The reason why I find the initial horizontal is because the horizontal component of a projectile does not change if there is no air resistance, which means Ux is same as Vx. Okay, so the kinetic energy at the highest point we saw was only contributed from the horizontal part, which is also half m Ux squared, which is what we found earlier. We have half m, what is Ux? Root 2 over 2 U squared. So then we say, okay, so now the kinetic energy at the highest point is half m. From this part, you will get 2 over 4 U squared. Okay, you're like, wait, that's nowhere near what we're trying to find. How do we get there? Well, we're almost there. If I rearrange this a little bit, you will find out that it is half m U squared. Okay. How do I get it in terms of E? What is E? E is the initial kinetic energy. So E is half m U squared. Which means I can substitute this equation, half m U squared, into my working. So half m U squared, so that's E. Which means the answer is 0.5 E. Dun, dun, dun. So that's answer A in this case. So what just happened? Well, we found the kinetic energy at the max point, but we need to get the answer in terms of E. So we need to find a way to substitute values to get what we want. So that's why we substituted this in, and then we substituted our value of E in based on what we know of the initial condition. Okay, so that's a projectile. So you need to revise a little bit more. Here's another question I made up, kind of, to think about projectile energies. So if we have a projectile thrown at some angle, who knows what, I don't care. At an angle, the projectile at some point in the picture has a horizontal and vertical velocity. What's the kinetic energy of the projectile? When they say kinetic energy of the projectile, they mean the V, not the component of the V. So if I draw the V, it's going to look something like that. I should touch the projectile path. So that V is the one that you want to plug into your half mv squared. So kinetic energy at that point will be half mv squared. Well, I need to find V. Okay, revision time. If you have the X and Y component, your V, let's write it up here. V is Vx squared plus Vy squared. Square root. Why is there a square root? Because if I redraw this, I'm going to have a vertical down by 10.1 and then to the right of 23.0. These are vectors, remember? So then your resultant, or I should say the V, is this one. It's like kind of combining your components. Component, combine. And you can do that by Pythagoras theorem because the components are always right angle to each other. Anyway, so we can do that. So we find our kinetic energy is half m times, what's the velocity? Okay, so we got to do square root square. Actually, the square root kind of goes away, but I'll write out everything. So 23 squared plus 10.1 squared. That's how we can find the kinetic energy. Well, we don't really have a mass. That's okay. I'll just leave it in terms of m. So I have 23 squared plus 10.1 squared the whole thing times 0.5. So roughly 315.5 m. M is a mass, whatever that is, how many kg I want to plug in. Okay, so this is a refresher. Kinetic energy, you're looking at the velocity, not the components, the resultant velocity. So how would you plot out then the graph of the kinetic energy for this projectile? In chapter 3, we very briefly look at the graphs and how they would look like. But now, let's take a proper look at how the energies would look like. So let's break it down into component first, so we can think about each component separately. So component in, let's say time. You can do it in terms of distance also. Let's look at the horizontal one first. So horizontal velocity, okay, I'll use green color. Now the horizontal velocity, remember, for the projectile does not change. It's same horizontal velocity throughout. So the horizontal kinetic energy is going to start off the same value and just be the same throughout the whole thing. This is your kinetic energy from, if you only look at your horizontal velocity. Kind of breaking it down. Well, kinetic energy doesn't direction, yes, but I'm just showing you how the energies change. How about the vertical? So the vertical is this 10.1. Does it change throughout the whole thing? Well, yes, it does, definitely. You start off with some velocity on the left, you end up with some velocity on the right, and you'll be 0 on top. So you will have some kinetic energy in the beginning. I don't know what that is. I'm just going to throw some values in. So let's say I start from there. It could be above or below depending on the question. So I'm going to decrease down to 0, because that is where the max height is, max point. And then after the max point, it's slowly going down faster and faster. So your vertical component is getting bigger. Let me draw everything out. Smaller, 0. So then you're gaining kinetic energy if you only look at the vertical part. Now if we put both together, what you're going to get is something like this. Let me rub this off. So this is the E if you look at only the X part, and the purple is the E kinetic energy if you only look at the Y part of the velocity. If you put it together, you get what we call the true kinetic energy of this projectile. Means the V lah. How does the V really change? It's basically adding up your X and Y together. So it's going to start with some initial velocity V, and it's going to go down. Will it go down to 0? Actually, no. It's going to continue going up. Why does it not go to 0? Because at the max point, you will still have a kinetic energy. Because, look at the top right diagram, the max point, you still have a horizontal velocity. So your projectile will never have a 0 kinetic in the air. Okay, it's always moving, even at the maximum point, because it still has, I shall label, still got vertical velocity. Therefore, you still have kinetic energy there. Okay, so this is the main point I want to help you review a bit, visit old concepts. Now we're adding on new ideas to them. So you're going to build up this knowledge slowly and carefully. So in this video, we looked at kinetic energy and how you can put in work to a system to change kinetic energy. So work done on a system with external force acting on a system can be equated to the change in kinetic energy of the system if it's moving faster and faster. So you will see situations where trolleys are moving, people are running, I don't know, trains are flying, well, not trains are flying, planes are flying, trains are rolling, things like that, all to do with kinetic energy. Say anything moves, got kinetic. So next up, we're going to look at potential energy, which actually has a lot of potential energy. The main one will be gravitational potential energy. And we'll also have a little bit, a very brief touch on electric potential energy and elastic potential energy, also known as spring energy. So we'll be focusing more on gravitational because the other two are saved for later. So electric is a whole chapter, spring is the next chapter coming up in AS. So this is, yeah, we'll see these ones later. So I'll see you all in potential energy.